So we have a sequence of numbers of 0, 3, 8, 15, 24, and a little dot, dot, dot indicating that this pattern continues. When being asked for a general term or explicit formula for a sequence, I'm going to default to general term in terms of the language I'm using. You could have constant addition, constant multiplication, aka this might ultimately be an arithmetic or geometric sequence. If you're constantly adding by the same number, you have a common difference, that's arithmetic. If it turns out you're multiplying by the same number over and over again, that's going to be a geometric sequence, which we technically have not learned yet, but that's what a geometric sequence is. You might have factorials in here, quadratics, cubics. It could be a lot of things. So always, we're in a textbook. It is introductory. Look at that idea of it being arithmetic or geometric. Is there a constant addition or constant multiplication? And if one of those two works, great. And if not, go to the next option that is the, simplest option. And then maybe you need to go to factorials. That's really common, right? We just got reintroduced to factorials, so they're going to want to bring those into our practice problems. Let's start with arithmetic. Look for a common difference. What type of addition do we need to do to get from, and don't forget, this is a sub 1 or n equals 1, a sub 2 or n equals 2, a sub 3, a sub 4, a sub 5, and so on. So we need an expression that turns an n of 1 into a 0, an n of 2 into 3, an n of 3 into 8, an n of 4 into 15, an n of 5 into 24. And you might just see it immediately, which is great if you can do that. But for those of us that cannot, start looking for a difference. So we have between 0 and 3, 3 minus 0 is 3, 8 minus 3 is 5, so we have an addition of 5. We have 15 minus 8, which is a plus 7, and 24 minus 15, which is a plus 9. And this is going to be called our first differences. I put that in your notes the other day. And if your first differences are constant, then the a sub n term that you ultimately create, the general term, is going to have a linear function in it, or an n to the first power, with some other, probably just addition and maybe multiplication. But those aren't constant. However, look at the 3, 5, 7, and 9. How do we jump between 3, 5, 7, and 9? You're adding by 2. So if we look at another difference, 5 minus 3 is a difference of 2, or adding 2. 7 minus 5 is a difference of 2, so 5 plus 2 is 7. And then finally, 7 plus 2 is equal to 9. So for this question that we have a second difference, which is constant. Therefore, a sub n is a quadratic function. Okay, so again, I'm just trying to talk to the thinking of this, not just spew out an answer. So a sub n is going to have some kind of math in it with an n squared involved somehow. So start mentally doing this in your head. 1 squared is 1. 2 squared is 4. 3 squared, right, because the subscripts are our values of n. That's our positive integer domain. 3 squared is 9. 4 squared is 16. 5 squared is 25. When I take these values of n, 1, 2, 3, 4, and 5, and I mentally square them individually, I get answers that are all what compared to 0, 3, 8, 15, and 24? Mia? One more. So it's n squared minus 1. And there's your general term. Now, what if this wasn't specifically asked by you all today, but for another example, what if we have 1, 2, 6, 24, 120? I'm scanning through the homework. I know you didn't have any like this. So take just take 30 seconds. Look at this list of numbers. What would the general term be? Is there a constant addition? Is there a constant second difference? Constant third difference? Is there a constant ratio? If not, look at some other ideas that you may be thinking that may be occurring. I just made this off the top of my head, so it's not the world's most complicated problem, but we didn't talk about one of these yet. So what expression would turn a n value of 1 into 1, a 2 into 1, a 3 into 2, an n value of 4 into 6, 5 into 24, and 6 into 20? Right? Because the domain of sequences is positive integers. What pattern do you see in these numbers, ma'am? I'm not asking for the final, I don't want the general term yet. But just as you see, just as you see 0, 1, 2, 6, 4, 24, and 120, do you see any kind of pattern of mathematics that you can take advantage of? So let's look at that pattern. How would you jump? And you don't have to start at the beginning necessarily. What kind of pattern of multiplication do you see here? Start anywhere in the list. You don't have to start at the beginning. You can even start at the end or the middle or whatever.
Well, I know at the beginning it's most likely times multiplied by 1.
Okay, so we have a multiplication of 1 to get us from 1 to 1.
And then the second one's multiplied by 2.
So then we're multiplying by 2 to get from 1 to 2.
Yeah, and then the third one's multiplied by 3.
And then multiplied by 4. And then multiplying by
5.
Okay. So what we're multiplying by is going up by 1. Did we just recently learn a new math function or review a math function that is some kind of repetitive multiplication with what you're multiplying by is changing by a value of 1? Exactly. Now, when we say factorial, like 5 factorial is 5 times 4 times 3 times 2 times 1. When we introduce a factorial notation, what we're multiplying by changes by 1 and we count down, not up. But 5 times 4 is 20, times 3 is 60, times 2 is 120. So we have a repetitive pattern of multiplication, but we're not multiplying by the same number over and over again like we would do with a geometric sequence. But we do, that is factorial. So, but we just said that it's 5 factorial that's equal to 120, and this is 6. What factorial would give us 24 then? Well, no, 5 factorial is 120, so that can't be that. It's 24 came from 4 times 3 times 2 times 1. So 4 factorial is 24. What about 3 factorial?
6.
Okay, and then so on and so on. 2 factorial is 2. 1 factorial is 1. And by the way, by definition, 0 factorial is also 1. So when n is 6, this is what factorial? 5 factorial. When n is 5, this is what? 4 factorial, and so on. So what do you think the a sub n expression is, ma'am? Okay, so that's what you think the answer is. Let's double check it. N factorial.
N minus 1 factorial.
Why did you change it?
Well, because it's not, because like 6 factorial isn't 1.
Yeah, this isn't 6 factorial, it's 5 factorial. This isn't 5 factorial. 5 factorial isn't 24, it's 4. So what?
N minus 1 in parentheses and then a factorial.
There you go. Boom. Nice job. All right, see you in a few minutes. Okay, so for our next problem, it would be 1 and then negative 3/4. And then 1/2 and -5/16, and so on and so on. So when you're trying to write a general term to a sequence and you start seeing fractions pop up, then you should be writing everything as a fraction and attempting to get either the numerator or denominator to be the exact same number across the board, which you would hope for with maybe a relatively, with one of the easier problems, or develop a very obvious, very simple pattern for the numerator or the denominator. But when you have sequences that start to involve fractions, then you want to have everything look like a fraction, and you want to handle the numerator and denominator as completely separate problems. That'll make it much, much easier to work these out. So how about the 1 is written as 1/1, -3/4, 1/2, -5/16, and so on and so on. And I want to try and make a very simple pattern show up in either the numerator or denominator. Let's say I'm going to try and make the denominators, because I see that there's a 2 to the 0, and I'm seeing a base of 2 in the 4 is 2 squared. And there's a base of 2 in the 16. That's 2 times 2 times 2 times 2, or 2 to the 4th. So I'm already starting to formulate a plan of how to do this, but then I've been doing this for like a way long time, and you're just sort of learning this for the first time. So what I might try is, I've got a denominator of 1, 4, 2, and 16. I'm going to start working some of the denominators to be closer together and see if I can start to see a pattern show up. Like maybe, since I have a denominator of 2, I don't write 1 as 1/1, but maybe write it as 2/2. Just to match this third denominator, not because I know where I'm going necessarily in the problem. Like, I can't look at all these and know the answer in 2 seconds. It only just seems like I can do that because I've worked in this book for years, and I've been teaching pre-calc for, probably 25 years. So you kind of get used to the patterns in here. So now, okay, I got 2, 3, there might be something going on here. 2, 3, 4, 5. Okay, so maybe I shift gears from trying to make a nice simple pattern show up in the denominator to, well, maybe if I just make this 2, 3, 4, 5, I'll start to have some kind of like revolution as to, or idea like, of what to do next. So let's make this 1 into a 4. But we're pretend like we're adding fractions. I can't just make the numerator larger without making the denominator larger, right? So if I multiply the numerator by 4, we have to multiply the denominator by 4. So we're going to sort of pretend like we're finding common denominators. And we're going to multiply the numerator and denominator by 4. So I can create that 2, 3, 4, 5 pattern. So now we got -2/2. That's positive. Let's try that again. Okay, maybe I need to go drink some water. I have my 2/2, -3/4, +4/8, and -5/16. And so on and so on. There are 3 things going on with each of these terms. You want to deal with the positive, negative nature as one problem. And you want to deal with the numerator as a problem. And you want to work with the denominator. I'm not sure how great all these colors are showing up, but those are 3 separate questions you want to deal with. And if that's my suggestion if you need to. Maybe I know some of us won't necessarily need to think about this as 3 separate problems, but how do we turn an n value of 1, 2, 3, 4? How do we turn a 1 into a 2 a 2 into a 4. I don't know why I picked the denominator first. There's nothing special about it. A 3 into an 8, and a 4 into 16. What's the pattern for that one, Zane?
You put a 2 underneath that.
Yeah, it's 2 to the first, 2 squared, 2 cubed, 2 to the fourth. And if you're still not seeing that, there is a multiplication of 2 to go from 2 to 4, right? 4 divided by 2 is 2. 8 divided by 4 is 2. 16 divided by 8 is 2. So whether you see the base of 2 in 2, 4, 8, and 16, or whether you repeatedly back divide and you see that repetitive nature of the multiplication of 2, our denominator is going to be a sub n is going to have a denominator which is 2 to the n power. How do we turn a 1 into a 2? A 2 into 3. I'm looking at just the orange part here, not the red plus or minus. 1 to a 2, 2 to a 3, 3 to a 4, 4 to a 5. What's happening to these values of n? What do we need to do to these values of n to make the numerators of 2, 3, 4, and 5? So the numerator is or has a factor of n plus 1. Plus, minus, plus, minus, plus, minus, plus. The only way your sign is going to alternate back and forth, positive and negative, is if you're doing what? Multiplying by negative 1. So our numerator has to have a factor of negative 1 in the numerator. Now, negative 1 to the power of 1 is what? Negative, not positive. Negative 1 squared is positive, not negative. So this exponent is not n. You need to adjust it a little bit. And I don't care if you do plus or minus. They're both right. But it's not negative 1 to the n. It's negative 1 to the, I don't know, I'll do n minus 1. So let's check it. N is 1. What's 1 minus 1? 0. What's negative 1 to the 0 power? Positive 1. N is 2. 2 minus 1? 1. What's negative 1 to the first? Negative, and so on and so on. So this is our general term for that problem. Good questions. Write the general term. This is how I'm going to put on the test. Write the general term of the sequence given by a sub 1 is equal to 81, and a sub k plus 1 is 1/3 of a sub k. This is the fourth question that we're doing that is asking for the general term, the a sub n term. How did the first three start? They gave you the list of numbers. So let's make this seemingly much different looking problem. Let's give it the same look. Let's write out the sequence. So what's that going to be?
81.
So the first number is 81, and a sub k plus 1. In subscript notation, when your sequence is, if you add or subtract 1, that's either the next one or the previous one. So a sub k plus 1 is simply the next number. Is found by doing 1/3 times the previous. So if a sub 1 is 81, then a sub 2 is what? Divide by 3. 27. Okay, a sub 3, do not look at her calculator. Divide by 3.
Isn't it 9?
Thank you. 9. A sub 4. 3. Oh, maybe we got one to now. Just kidding. I love you so much. What's the next one? Yes. Okay. And then the next one's going to be 1/3. All right. So, and this sequence of numbers goes on forever. So, we want to, make a 1 into an 81. Arguably, that's already done. A 2 into a 27. A 3 into a 9. A 4 into a 3. A 5 into a 1. What is this What type of equations are we given here for this sequence? What's the vocab word? What are these? Come on, read your notes. What are these up here? This sequence is described or given to you with a set of, these are recursive formulas. If you want the next number, just keep dividing by 3. That's what it was doing to tell me that, the next number is 27, the next number is 9, then 3, then 1, then 1/3. So what is the general term? Okay? To write the general term, you can use the pattern that's given or recognized to, kind of blend the idea of a general term with recursive. Like, you multiplied by 1/3. We multiplied by 1/3. We multiplied by 1/3, and so on, and so on. A sub n, you can kind of lean on that idea of the recursiveness. A sub n, your general term will start with the first number, 81. And to get to the second number, how many times did we multiply? And oh, by the way, we are constantly multiplying by 1/3, right? So Daniel, when you constantly multiply by the same number, what does that give you? What kind of math symbol does that give you? 4 times 4 times 4 times 4 times 4 is 4 to the what? Exponents are repeated multiplication. So if we are repeatedly multiplying by the same number, it's going to be 81 times 1/3 to some exponent. When n is 2, for the second number, how many times do we multiply by 1/3? Once. To get to the third number, when n is 3, how many times do we multiply by 1/3? Twice. Fourth number, n is 4, 3. When n is 5, the fifth number. So what do you think the exponent is? How many times do we multiply by 1/3? There you go. Bam! N minus 1. And that is your general term. And we could simplify it to another look, another appearance, another equation, but that's it. That's sufficient. Zane.